Greetings, AP Chem. Today we're going to be talking about what I call Unit 9. Now that doesn't match up with the College Board units, but what it does match up with is our extension into equilibrium. And so after we talk about equilibrium in general, we are going to be talking about solubility. And solubility starts off by talking about this thing called the KSP value. So that's what we're going to get into today, kind of talking about the basic introductions to those things, and I'll show you how to do some math problems with these. So if we think about the K values that we've talked about before, we've talked about how there could be a KA, there could be a KB, a KC, a KP, and a KSP. Now, a KSP stands for something called the solubility product. And you say to yourself, solubility sounds vaguely familiar from earlier in the year, and it should, because this has to do with the solubility rules that you used earlier in the year when we were talking about precipitation reactions. And so what KSP processes deal with are ionic compounds that if we used our solubility rules, we would consider them to be insoluble. So like when you thought about your precipitation rules, they're the ones that make the precipitates. And here's the, I guess, dirty secret about these is that when we say that they are insoluble, for the most part, that is true. So if I take a look at the solubility rules and I figure out that this compound is insoluble, it is going to form a precipitate if I have the right amount of stuff there. But to say that it doesn't dissolve at all is actually kind of a little bit false. It dissolves just a minuscule amount in solution. It just doesn't dissolve very noticeably. And so when we talk about KSP, KSPs are dealing with salts that don't want to dissolve very easily. And what we're going to do is use this to calculate the solubility of those very insoluble salts. Now we talk about molarity if something is soluble because we can just measure the moles on moles on moles. However, in this case, we've got to use this KSP value to figure out how much is dissolved because it's not that much. It's not all 100% to product like we're used to when we talk about making a normal solution. So we're going to take a look at two different salts. And the first one is just literally salt NaCl. You know, with your solubility rules, chlorine is a halogen, and halogens are going to be soluble unless they're paired with lead, silver, or mercury. And so it's with NaCl here. Na is soluble basically all the time. And so what happens is when we put NaCl into water, it's going to dissolve until the solution becomes saturated. And in this case, it's going to dissolve a lot. The reason that happens is because the new attractions that water makes with the ions are stronger and more favorable than when it sticks together. So you can think about it as the attractions here are basically more favorable to break apart into ions than they are to stay stuck together. And so when we think about making salt water, we can make that really easily. It should dissolve, quite a bit in when we dissolve it into water. Now, on the opposite side of that is lead fluoride. Now, fluorine is also a halogen, but when it's partnered with lead, it becomes insoluble. And so this picture here off to the right-hand side, I think, does a good job of showing what that looks like. The lead and fluorine ions really want to stick together and are more attracted to each other than the benefit that they get from dispersing. If you think about this in terms of their entropy, it's better for them to stick together, even though entropy would be better to kind of break apart. And so we would still have our waters attached here, but when we think about how much can dissolve, in the case of lead fluoride, it is much smaller in its quantity because it has these attractions that don't want it to break apart. And these are the scenarios that we're going to talk about with KSPs. Now, in previous reactions, we've talked about how when we have a salt that can dissolve, it breaks up into its component ions. So in the case of this lead fluoride here, we would have the Pb+2 ion and then 2 fluoride ions, which are F-. And that's the equation we have here. So when you're dealing with a solubility and a KSP problem, the way that they make the solutions is identical. When they are able to dissolve, they break up into their ions in their respective charges and quantities. But what's happening here is that it's just a teeny tiny amount. And the teeny tiny amount that is there present at that point in time has to do with the KSP value. So when you look at a chemical reaction for a solubility like this, you have to think about it like an equilibrium reaction. We've got the double-sided arrow, which means that we get a little bit out as product, but some of it is also remaining as a solid. And our KSP expression is going to look a little bit different, and you'll see more of the power showing up when we talk about the KSPs. So in the case of this reaction, it's the KSP equals the concentration of Pb plus 2, right? Matches the ions here, times the concentration of F minus. And in this case, because there's a coefficient of 2 here, it's going to be squared. Note in this case also, we do not have a denominator, and that's because we have a solid here on our reactant side. So that solid doesn't get included in our equilibrium expression. And KSPs do not have a denominator. So the expression is always the ions here. Now, things I see people getting tripped up on is we forget the charge. We don't put them in there. Or you put the 2 in front of the F here instead of as the coefficient. That 2 is going to show up when we do the math for these, but in general, in your expression, you leave it out of the actual expression other than putting it here as the square, okay? So when we're talking about solubility specifically, it's just dealing with those insoluble salts, okay? So what we need to do then is we need to get into the math of this. So the example that I'm going to go through is this one. It says, what is the solubility of PbF2 at equilibrium if the KSP equals 4.1 times 10 to the negative 8th? And just so you know, with KSP values, they tend to go very tiny with the exponents, and we'll talk about that after we work through this example. And then the question also is, what would the concentration of F minus be at equilibrium? So we are going to get to our all favorite doc cam here and then work through that. So in this problem, we have our KSP given to us, and we have ours asking for our solubility. When we are dealing with these, solubility in our problems, if you think about our ice table, is always equal to X. I'm gonna make sure I've got this ratio change, otherwise this is gonna be a problem. Okay, so when we talk about solubility, solubility in our KSP is always our X value. So if we are looking for what the solubility is going to pop out usually in moles per liter. It's how much of that stuff actually dissolved in a liter of that solution. And then it is going to be the X value here. So what we need to do is we need to set up our equilibrium reaction and then get our ice table set up for this. So I'm going to break up my ions just like I did in the equilibrium expression we had before. I got the Pb plus 2 ion and then the 2F minus ion here. Okay. Now, if I want to find my solubility, the solubility is the X, and I've got to find that by structuring my ice table and organizing it. Now, in the ice table, if I have a solid, I ignore that the entire way through. So I'm just going to draw a line because it is not relevant to my equilibrium expression or anything like that. And when we are talking about solubilities in the beginning, if there's nothing present in the beaker other than that particular compound that's trying to dissolve a teeny tiny bit, I'm going to put my concentrations here at 0 to start off with. That's going to change when we deal with other things, but right now it's at 0. Okay. Now, if you remember, the changes in this case have to be positive because I have nothing here, so we have to make some product, and it's going to be a plus X here for Pb plus 2, and it's going to be a plus 2X for my F minus because of the coefficient here. So equilibrium is going to be X and 2X for each of these. Okay. So what I do then is I'm going to take my KSP expression and set it equal to these guys here. So my KSP expression we talked about was concentration of the Pb2 plus ion times the concentration of the F minus ion squared. And that whole thing is equal to my KSP value, which is 4.1 times 10 to the negative 8th. Okay, so equilibrium values go into my expression. X for Pb plus 2, and then 2x for F minus. But be careful when you put this in here because it's 2x and then the 2x term is squared. People really mix this up a lot and they will just write in 2x squared, right? But 2x squared is different than 2x in parentheses squared. It seems like semantics, and it is, but it's going to give you different math. And so again, that whole thing is equal to 4.1 times 10 to the negative 8th. Okay? So that is my equilibrium expression with my equilibrium values put into here. What that's going to give me is x times, see, I'm already making mistakes, 4x squared here. And that's equal to 4.1 times 10 to the negative 8th. And so I end up getting 4x cubed equal to 4.1 times 10 to the negative 8th here. Now, I know that that's a lot of math, but I'm just kind of showing you how this all shakes down here. You will see some common numbers showing up in your equilibrium solutions here for these things. 4x cubed is one you're going to see a lot. You will see x squared. You will see 27x to the 4th a lot and 108x to the 5th. And in the next video, which will be a very short one, maybe I'll throw it on here, but I think I'm going to run long. I'll show you kind of where those come from. Okay. So when I get into this, now it's an issue of just solving. So I'm going to divide both sides by 4. And you don't have to show that work. I'm not going to show that work either. I'm just going to show you how I get to x cubed equaling 1.025 times 10 to the negative 8th. And now I need to take the cube root of this. This may be kind of tricky to find in your calculator, so that's going to be up to you to find that. But you could also take it to the 1/3 power if you needed to do that as well. So in this case, x is equal to 0.00217 molar when I take the cube root of both sides of this. Okay, so that's my concentration. What this means is that in 1 liter of PbF2, which doesn't get a whole heck of a lot dissolved, if I have 1 liter of that, the concentration of the moles of PbF2 are going to be 0.00217. So the concentration of the PbF2 is that. Now, here's the deal. As long as there is solid sitting at the bottom here, the concentration will be 0.00217 if I have 1 liter. It would be that if I have 100 liters. So as long as I still have solid at the bottom and we have what we call a saturated solution, which you may remember from your general chemistry class. If I have a saturated solution, it means that I have as much of this dissolved as possible. So my PbF2 here, that is going to be 0.00217 molar as long as there's some solid left that can dissolve. It will saturate that solution and be like that, okay? That also means, if you think about how our ice table was set up, the concentration of lead is equal to X as well. So not only is this the concentration of PbF2, it is also our concentration of the lead ion, Pb plus 2. Okay, so if you just think about how these work, since I make 1 lead ion for every one of these that I dissolve, I'm going to have the same concentration. F minus, though, its concentration was equal to 2x. So it's equal to 2 times the value because I have 2 F minus ions coming in there. So in this case, it's going to be 2x. So if I want to find my concentration of F minus, what I've got to do is I'm going to take 2 times my X value, 0.00217 molar. So my concentration of my F minus, the fluoride ion, is actually going to be 0.00434 molar. It's twice as much. And that's because I get twice as many ions made here as I'm going through. Okay? Hopefully this makes sense. Now, College Board, once they figure out how much this concentration value is, they could use you or ask you to do a problem with this molarity that would say, like, how many grams are dissolved? And then you'd have to use the moles per liter, then get the moles and turn to molar mass. So that's stuff that we will be practicing in class, but be aware that this will oftentimes be the first step of this problem, and to pay attention to the coefficients here. Anytime you find X, X is my solubility. Okay, so that's the solubility. That's the overall solubility of the whole compound. The number of ions will tell you what the concentration of each of those are. Again, if I keep adding water in here, as long as there's more solid that can dissolve and it stays saturated, my solubility is still 0.00217 molar, because that goes back to that equilibrium constant. If you think about Le Chatelier's principle, if I dilute these all of a sudden, this solid is going to turn into ions to compensate for that and get back to equilibrium. So that is kind of what we're going to deal with there. We're going to take a look in our next video at a very quick little thing about comparing KSP values, and then we will go from there. So if you have any questions, please let me know. Otherwise, good luck.